Hi, I'm Andres. First of all, I would like to thank the organizers for putting together this lovely workshop, as well as for giving me the chance to present this work here. Beforehand, I also would like to apologize because this is a pre-recorded video, and this is basically because, well, unfortunately, and due to the pandemic, I'm in a place with a very weak internet connection, and therefore this was my only reliable option. Right. With that out of the way, today I'll talk about this work on quantum resource theories, where we provide an operational interpretation of a resource quantifier. And well, this is a joint work with Paul Skripczyk. Right, so this is the outline. First, I'll be going through quantum resource theories. Then I will introduce the operational task of quantum state exclusion, the resource quantifier of weight of resource, and then we will move on to our main result, which is basically connecting um, state exclusion games to this quantifier of weight. And finally, well, I'll present some conclusions and some related work. Right, so if we start with quantum resource theories, one way to approach this framework is by first defining the objects of the theory. In this talk, we will be considering the objects being measurements. Well, it has to be said that, well, in our paper, we actually address measurements and states, but well, in this talk, we will only be discussing the measurements. And well, as we know, a measurement or a POVM is a collection of operators such that they are positive semi-definite and they add up to the identity. So the objects are measurements, and then, well, in a commonly in a resource theory, we then define a property of these measurements such that objects that they satisfy that property, we will call them a resourceful measurement, and then, well, the objects that do not satisfy a property, we will call them resourceless or free measurements. In this case, we will be addressing as a property any we will consider any convex set of measurements, and we will denote it as f, and we will call them, well, we will call them free. And in this diagram here, this is the ellipsoid in the inside. This is the set f, and then what this effectively divides the space of all measurements into two sets: resource free measurements and resourceful measurements. And in this particular case, this point m here, this measurement, well, it's going to be a resourceful measurement. Usually in resource theories, we can also address, well, a myriad of other points of interest: resource quantifiers, operational tasks, free operations, and so on. Well, I invite you to check this recent review on resource theories for more information on these points. Right. So now we will move on to operational tasks, where the objects of interest are measurements. This is called quantum state exclusion, and it was proposed in 2014, and it's basically the following. The task or the game involves two agents, a referee and a player. So the referee is in possession of an ensemble of states, here represented by rho x, which are distributed with a probability distribution p. Then the referee sends one of the states to the player, say rho x, and then, well, the player is going to implement a measurement m, and it's going to measure the state that the player received, and then, well, it's going to obtain an outcome a, which he's going to use to generate which is, well, given, as we know, by means of the Born, with a probability p given by the Born rule, which is given by this expression. And then with this outcome a, the player is allowed to post-process this outcome to generate another one, g, and well, with a probability q of g given a, which is an arbitrary probability distribution, and, well, this output g is basically going to be the guess of a state that was not sent. This means that the goal of the game is for the player to output an index g such that it will be the players guessing on the state that was not received. So in other words, the referee is going to determine that the player succeeds if this output that the player generates G is different than X. And well, it's going to fail otherwise. We can think about this state exclusion game as being opposite to state discrimination, because as we can see here, the referee is penalized when the player is penalized when he actually guessed correctly the state. So, well, taking these steps into account, we can define the figure of merit in this task as a probability of error at state exclusion, and is given by this expression where here we have the p, here we have the measurement basically given by the Bond rule, where index A is generated, then the player is gonna post-process this outcome A in order to generate an outcome G, and then well, the winning condition, the losing condition in this case is for that G to be equal to X, and therefore the losing condition is just a delta. And then well, this minimization is basically telling us that we allow the referee to implement any classical post-processing queue, which is the one that appears here. Right, so this is the probability of error state exclusion, and it's going to be, well, the figure of merit that we're going to be interested in. Right, so now the motivation is to, within this task, to compare a player using free measurements, which we will call a resourceless player or a free player, against a player that is able to implement any measurement, potentially a resourceful measurement. So we want to compare these two types of players, and then, well, a free player, a resourceless player, in principle, we're going to allow this player to implement any free measurement, and therefore, well, the player is interested in minimizing the errors, so in minimizing the probability of error for a given game E, which is, well, an ensemble. And then, well, that is, this PC will be somehow the classical or the free somehow strategy. On the other hand, a resourceful player, well, is going to be allowed to implement a fixed measurement M, potentially resourceful, and well, in this case we just apply the whole definition that we had before. Right, so well, that is it. And then well, before we move on to somehow characterize this task, I think it is illustrative to present the state of the art before we started to address this problem. And then it is the fact of, well, comparing resourceless players against resourceful players, like by means of operational tasks. So, well, we have these two results from last year, which they basically they somehow derive a three-way correspondence between operational tasks, in particular quantum state discrimination, resource quantifiers in the form of the robustness. This is a function of the measurement. And then this third other side, which unfortunately I don't have much time to talk about, but it is related to information theoretic quantities. So this was somehow the state of the art. And then, well, of course, now we are discussing another operational task, which is different than quantum state discrimination, which is quantum state exclusion. And then, well, in that case, the motivation is to see whether there can be a quantifier here characterizing this task in the same way that the robustness is characterizing quantum state discrimination. Well, Skripcek and Linden, the intuition was that that was the case, that not only discrimination but other tasks. And then well, the main question of this work was basically, well, trying to identify which one was that, if any, was that quantifier. And then, well, spoiler alert, the answer it is going to be what it is called the weight of resource, meaning that we didn't have to invent or like any contrived like quantifier there. If curiously enough, it was something that it was already known in the literature. So let's see. So, well, the weight of resource in principle is a function on the measurement m. So given a measurement m, this function is going to give us a positive number, which is which can be written like this. In principle, we are asking for the minimum value w, such that each POVM effect can be written in this form, and we can see that the w appears here. So it can be somehow be seen as the amount of this measurement that has to be used in order to recover my measurement of interest, and we can see that in a geometric way. Again, this ellipsoid represents the set of all measurements, f the set of free measurements, and well, the rest, the complement is going to be the set of resourceful measurements. Here we have m, and we are asking for the compositions of the way n and mg, when n is a free measurement. And then we ask, amongst all of these decompositions, among the one that has the least, the shortest distance here between m and f, and then somehow this distance it is related upon modulo a factor here. Well, this is related to this distance. So this is somehow the operational. This is somehow like in understanding this function as a distance. And then, it has to be said that, the first, here we are implementing it for measurements, but the first time such a quantifier was used was by the EPR2 article in 1991, where they implemented it in the context of Bell non-locality, as well as in 1998, where Lewinstein and Sampera introduced it in the context of entanglement, and this case is also known as the best separable approximation. And so just to say that, it is something that it was considerably well known, and that here we're only considering it for measurements. And then, this quantity is a good quantity because it satisfies some desirable properties. It is faithful, meaning that it completely characterizes the set of free measurements, as in it assigns the value of 0 to any free measurement. It is convex, meaning that the mixture of measurements do not increase the amount of resource. And then, monotonicity for a desirable order between measurements, and it means that the function respects the order. Right, so that is the weight. And now, again, coming back to our main motivation, which is to compare any resourceful player against the best resourceless player. And then we have the first result here, which is that this for any measurement m, there exists a game such that there is this strict inequality here, meaning that the measurement m is always, for this particular game, we see that we're playing the same game, is always better than any possible free measurement. This is a strict inequality, and this means that we have less errors when playing with m. And then we can rewrite this in this way. And here, when we are at this point, we are interested in seeing what is the best case scenario for the measurement m, meaning that we are interested in minimizing this ratio, which is what we have here. We want to know what is this minimum amongst all games. And then, our main result is that this quantity, which is in principle, completely operational, this quantity is characterized by the weight of resource, meaning that there is a function here which involves this function of weight, and then in this way the weight is characterizing this operational task. This is our main result, which somehow then answers the question of the quantifier that is associated to exclusion is the weight, and we have this result. To compare it with what was already known between discrimination and robustness, we have this. And then, unfortunately, I don't have time to talk about this third part, but then, we also can complete the triangular correspondence, but now for exclusion. Finally, as I mentioned at the beginning, here I talked about measurements, but in our paper, we addressed measurement and states, both for general resources. And then the conjecture is that this applies to other resource theories, and then in particular and in parallel to our work, Rupi and his colleagues derived the case for channels, which is slightly more general than our case, although they didn't consider the triangular correspondence. So we overlap, although we overlap on the operational interpretation. And then we also have this for multi-object resource theories and for Buscemi non-locality. Well, with that, I would like to thank you for listening.